Alright, this is the third video on Chatelier's principle. We've talked about how varying the concentration of the reactants and products can create a stress on a system in equilibrium, and how that system will shift in such a way as to relieve that stress. In part two, we discussed how pressure can affect equilibrium, and that it can have no effect if the number of moles of gas do not change from the product side or reactant side to the product side. But if there is a different number of moles of gas on one side of the equation, then pressure will affect that system. So the third stress that I want to talk about is temperature. And temperature is different, or affects the equilibrium constant differently than pressure or concentration, because temperature actually affects the rates of reaction. We learned that when we talked about kinetics. And the rates of reaction are part of what determines the equilibrium constant, or they do determine the equilibrium constant. And so temperature actually affects the equilibrium constant itself. So when we're talking about temperature and Le Chatelier's principle, what I usually like to do is I like to draw a box and then inside of a larger box, like so. And this inside box represents the reaction, like A going to B. And we call that the system. That's what we're interested in studying. And then outside of the system, all of this is considered the surroundings. And you'll have to forgive me on my penmanship here. I'm writing on a tablet that I can't see what I'm writing except looking up at the screen, so there's this disconnection between my eyes and what I'm moving on the pen. Alright, so let me put my double-headed arrows to say this is reversible and that equilibrium can be established. So when A reacts with B, we can have an exothermic process or an endothermic process. Exothermic means heat is released to the surroundings. So here's the system, and as A reacts with B, heat is released to the surroundings. If heat is released to the surroundings, we show that by the symbol delta H, which is called enthalpy, and it is heat released at constant pressure conditions, which would be like reacting A and B in a beaker, and we're assuming the atmospheric pressure is not changing through the course of the reaction. And because it's exothermic, we give it the delta H, or the change in heat, a negative value. It doesn't mean less, it just means that well, it can mean less than that the system has lost heat to the surroundings. But that's the convention we use. We just use a negative symbol to say that heat was released from the system to the surroundings. And this is called exothermic. I'll just say exo for short up here. Exoskeleton, outside skeleton, exothermic, the heat's released to the outside. Alright, so another thing I want you to think about in terms of heat is this. When we talk about, like, let's say the temperature of water, so we got temperature in degrees Celsius, and we've got time here in seconds, or it could be minutes. And let's say we start with water at 80 degrees Celsius, and we're going to cool it down. Let's say room temperature. Room temperature is 25 degrees Celsius. Tell me what a plot, if I recorded temperature every 10 seconds, or let's say every 60 seconds, tell me what that plot would look like. What would the graph look like? Would it be a straight line, or would it be a curved line? Well, hopefully you said it would be a curved line, like so. And we never would really, if this was 0 degrees, we would never reach 0 degrees, right? Because room temperature is 25. Now the question is, why is it steeper up here and it flattens out here? Well, the water up here has a higher kinetic energy. It has more energy in it. The molecules are moving much faster because we are at a higher temperature. And so remember that if two bodies are in contact with one another, in this case the water and the surroundings, heat will flow from the higher temperature to the lower temperature until they reach the same temperature. Well, initially this is faster because the water has more kinetic energy, but as we approach room temperature, there's not as big a difference in the kinetic energies, and we see this reaction come to equilibrium. So thinking about this and thinking about this problem up here and the relationship between temperature and the equilibrium constant, if we increase the temperature of the surroundings, what's going to happen to the equilibrium constant for this reaction? Do you think the products will be favored more, or do you think the reactant will be favored more? All right, so we know the equilibrium expression for this reaction is K equals, we could do, if we'll just say with the concentration B, concentration of B over the concentration of A. So we change the temperature, which actually changes the equilibrium constant. We raise the temperature. If we raise the temperature, it's going to be harder for this system to release the heat to the surroundings, right? Because the surroundings, if they're really if they're higher in temperature than the system, the heat will want to flow this way, right? So if that's the case, if the temperature was higher then the system, and the temperature starts to flow into the system, that's a stress on the system. So how is the system going to relieve this increase in temperature? Well, it's going to have to go in reverse, right? B is going to have to go back to A, which would absorb heat. So in exothermic reactions, that's the key here, reactions where heat is generally given off, when we raise the temperature of the surroundings, the equilibrium constant will decrease. So if the equilibrium constant decreases, we can see it like this. If we say K is equal to 4, and we had a ratio of 8 molar over 2 molar initially, if we raise the temperature, K decreases to, let's say, 2. So these numbers have to adjust. Maybe this goes to 6 molar and A goes to 3 molar, which would give us back to the equilibrium of 2. All right? So this is what you need to remember. For exothermic reactions, symbolized by delta H, or enthalpy, with a negative change or a negative value, as the temperature of the surroundings increase, the equilibrium constant decreases, and therefore the reaction is going to have to go in reverse. B is going to have to form more A to relieve this stress of the extra temperature. Now, endothermic. Endothermic is just the opposite. It's when A goes to B and delta H for this reaction is positive, and instead of the, let's change the color so we can still stay with the same diagram up here. Instead of heat going out of the system, heat goes into the system. That's an endothermic process. It's like when you put your hand on a cold glass of water, you feel the coldness of the glass because the heat is flowing from your hand into the glass of water. And it will keep doing that until the temperatures would be the same. But that doesn't happen, right? Because you're going to take your hand off the glass, or your body's not going to chill down to 37 degrees anytime soon. But that's an endothermic process. You feel the heat goes from the surroundings into the system. And we symbolize that with the delta H positive. The system's internal energy is increasing. All right, so for this, if the temperature goes up, what do you think is going to happen to K? Well, K is going to go up. K is going to go up. So we go up to maybe 10 for K instead of 8, and we get something like maybe 10 molar divided by 1 molar for equilibrium. So we see the reaction go in the forward direction. A goes to B, and it absorbs this extra heat that's coming in. All right, the extra heat coming in by the rise in temperature of the surroundings. The heat will flow from the higher temperature to lower temperature. It flows into the system, and that favors the reaction going in a forward direction for an endothermic process. All right, so you need to know how temperature affects the equilibrium of a reaction. And what I want you to remember, know these things. Know this for exothermic, and know this for endothermic. And just keep in mind that what's different about temperature than concentration or pressure is temperature actually changes the equilibrium constant. All right. One last system I want to talk about to finish Le Chatelier's principle, and that is what happens if you add a catalyst to the system. All right, so again we've got A going to B, and K for this is B over A, and I should make this double so we can, it's reversible. All right, so if we look at this reaction, let's say it's exothermic reaction. So here's reactant A, here's product B. The y-axis is energy, and the x-axis is reaction progress. So we got A, and we go over an activation energy, and then we form B. So this is what our plot would look like as we monitor the energy exchange as A goes to B. And if you've had kinetics, you know from here where A is to the top of this peak is called the activation energy. And a catalyst, what it does is it alters the reaction mechanism and lowers the activation energy, like so. So the question is, how does that affect equilibrium? If we have equilibrium established between A and B, and we add a catalyst, what is the effect? Well, if the reaction was initially started, it would cause B to form much more readily because it doesn't have to overcome this barrier, a highest barrier as without the catalyst. But as far as equilibrium, it lowers the activation energy to go in the forward direction, but it also lowers the activation energy going in the reverse direction. So a catalyst has no effect on the equilibrium. Catalyst speeds up the reaction because we got enough particles with enough kinetic energy to overcome this smaller barrier versus the uncatalyzed barrier. But same thing with B. If we were doing this in reverse, we would calculate the activation energy from where B is to the top of the peak, and a catalyst also lowers the activation energy from B going back to A. So catalyst has no effect on the activation energy. This has been the third video on Le Chatelier's principle, and next we'll be talking about equilibrium and acids and bases. Thank you.